All right, so for this question, 2.39, you have a giant sphere that is, importantly, it's neutral, but there's two hollowed out cavities inside. That was a terrible circle. Two hollowed out cavities inside, 1 and 2. And inside of each of these cavities is a charge, QB. Well, I guess I'll just label it as QB and QA. And furthermore, they tell you that the radius of this one is A, and the radius of this one is B, and the radius of the entire sphere overall is capital R. Okay, so that's our starting point. So now let's just go through the problems. So question A. Question A says, find the surface charge densities, what is that, sigma A, sigma B, and sigma R. Well, the, how do I phrase this? The sigmas are simply a measurement of, how do I phrase this? Okay, so if you remember, lambda in the very first practice problem was just a simple line. That's equal to the charge over the length. Sigma is the charge over an area. And in the last problem we did with Gauss's law with a volume, rho is equal to the charge over the volume. So in this case, what we're dealing with is sigma, so that's the charge over the area. Well, let's look at sigma A. How much charge is enclosed within this sphere? It's easy enough. It's only QA. So QA. And what's the area of this enclosed circle here? 4 pi A squared. Okay. What is the sigma or the charge density for B? It's almost identical. It's QB over 4 pi B squared, right? It's just the charge over the area. All right, so now what about sigma R? It's exactly the same. That's the nice thing, right? So it's just the charge over the area. Well, what's the total charge of R, this entire thing? Well, there's two. There's QA and QB. So the total charge enclosed within that is just QA plus QB. And then what's the area? Well, the area is 4 pi capital R squared. And that's it. You found sigma A, sigma B, and sigma R. Part B of this question asks us, what is the field outside of the conductor? Well, we can use Gauss's law. So if you want to use Gauss's law for this, let me rewrite Gauss's law. So Gauss's law says the integral of E times dA is equal to the charge that's enclosed over epsilon naught. So in this case, I'm going to just pick a point right here. That's my point I want to figure out the electric field for. It's outside of the conducting sphere. So I'm going to draw my Gaussian surface around. I'm going to say that it has a radius of little r. And then we can apply Gauss's law. So let's do the left side of Gauss's law. Again, like I said in the last video, the point of Gauss's law is that if you make a Gaussian sphere at that point you're interested in, every point along this sphere should have the same electric field because it's equally far away from the center. So this electric field pops out of the integral because it's a constant. So you just have E times the integral of dA, which just gives you E times A, which is equal to E times 4 pi little r squared, the area of our Gaussian circle. That's going to be equal to the right side of Gauss's law, the Q enclosed over epsilon naught. Well, what is the charge that's enclosed? It's just QA plus QB. Those are the only two charges, so those are the ones that are enclosed. All right, so now we have the left side of the equation and the right side of the equation, and let's just solve it for E. So E is going to be equal to, let's bring that 1 over 4 pi r squared over. and you still have left QA plus QB all over epsilon naught. Now, technically, you're done. You have your equation for E, but of course, typically it'll be written like 1 over 4 pi epsilon naught QA plus QB over R squared. That's the more appropriate way. We essentially just swap the position of those two. All right. Question C asks us, what is the field with inside each cavity? Well, this is also just using Gauss's law, and is pretty straightforward. So I will do it the long way for one of the cavities, but then it's just repeated for the other. So Gauss's law, E dA is equal to the charge that's enclosed within our Gaussian surface divided by epsilon naught. So I want to figure out what is the electric field inside one of these cavities. Let's just pick this point right here. We draw our Gaussian surface. We give it this Gaussian surface a radius r. Going back to our problem down here. This just leaves us with E times 4 pi r squared. Again, it's identical to the other side. The electric field pops out, and you're just left with the area. All right, so now we just look, what's the charge enclosed? Well, the charge enclosed of this little cavity is just simply QB. So the charge enclosed is just QB over epsilon naught. So now we just solve it for electric field. So the electric field will be equal to 1 over 4 pi epsilon naught QB over R squared. Now, if they want to know what the electric field is maximum, meaning like, take your Gaussian surface all the way to the edge of the cavity, then obviously your radius would just be radius B, but it doesn't really actually matter. Now, the cavity A is identical, so the electric field in cavity A is 1 over 4 pi epsilon naught QA over R squared, right? Because the charge enclosed with the other cavity would just be the other charge. Okay, question D, or part D, I should say. So part D is more conceptual, so there's nothing really to write, so I'll just explain it. So the question says, what is the force on QA and QB? The answer is 0. Now, the reason why it's 0, there's a couple of different ways to think about it, but the easiest one is this. If there's a charge here in the center, notice what that's going to do is cause essentially charges from this material, this sphere here, to build up on the cavity here. This charge essentially is going to be creating an electric field that's going to be pulling charges from the neutral purple sphere itself, so that they are all just sort of sitting on this cavity. But they don't just sit randomly. It's not like there's going to be more of them, like more electrons on this side of the cavity and less on this side of the cavity. So everything is going to be equal. Well, if everything along this cavity has an equal amount of electrons, that means that the pushing and pulling force between each individual electron is all equal. They all counteract each other. The same is true for the other cavity. So that means that individually they're not receiving any force. So if there's no force because everything is sort of equal along this sort of inner cavity, then that means that there's no force acting on them.